This is a picture of a bombardier beetle. It is shooting chemicals out of its abdomen there, and it looks really strange, just spraying some white fluid. What you're not seeing on the other side is that these two chemicals are housed in separate chambers inside of its body, and when they combine in the outside air in the presence of oxygen, they ignite. And so it's a defense mechanism that he can spray this chemical and it creates a flash of fire, basically a hot thermal exothermic reaction, a little explosion in the face of a predator without destroying him, because by the time the fluid gets past his body, that's how slow the reaction takes. It's only a millisecond, but it's slow enough not to incinerate him, and it happens well outside of his range. So this is the type of chemistry that we're interested in biology, of how living organisms are sustained by chemistry, founded in chemistry, and actually use it to pull off things like homeostasis, metabolism, all these words that you learn in science class. So I often say that biology is the most sophisticated of the sciences only because it's multidisciplinary. Physics is the foundation. Everything relies on physics. It's the base, it's the bottom, and it's fundamental. Chemistry relies on physics, and biology relies on physics and chemistry put together. And so biology is an emergent science about an emergent phenomena called life that depends on chemistry, which depends on physics. Now, we don't go all the way down to the physics level. We will a few times when we're splitting atoms and running electrons through membranes, but most of our interest is in the chemistry aspect of life, and so that's what we're going to introduce today, and then we'll explore more throughout the year. So let's do some very, very basic review to make sure that we are using the same terms in the same way in our class. So matter is made up of something called an element, like an elemental substance, which means it cannot be broken down any further. If you have a pound of gold or an atom of gold, it's still an atom of gold. It's gold is gold. A compound, in contrast to that, is going to be something where you take two or more elements and you put them together in a certain mathematical ratio. And this is what the cool thing is. Once again, emergent properties arise out of this. Now, I mentioned earlier briefly that life is an emergent property itself, and we see this first happening within chemistry. And so here's an example. On the left is this flaky, soft, silvery metal called sodium. Next to that is this yellow, clear, poisonous gas called chlorine. You put this flaky, soft metal and this poisonous yellow gas together, and you get table salt, something you sprinkle on your Hot Pockets or mac and cheese all the time. Now, I know chlorine is toxic because it used to service pools, and I would have to open up the chlorine tab case where they kept the large white tabs in there. But I always depressurized the system first. One time I didn't, opened up the little column, and the chlorine gas hit my face, made it all go dry, burned my eyes, and everything. So it is amazing, phenomenal, and strange to me that we will take flaky metal, poisonous gas, put them together, and it's safe to eat. And this is due to emergent properties. Biology is going to take this idea of emergent properties to a whole new level. Now, this is not a mystery of why this happens. It all has to do with bonding. And so sodium and chloride come together through what's called an ionic bond, and we will talk about the several different types of bonds. They go in this order: covalent, which I'll show you in a minute, but covalent is the strongest. Ionic is the middle of the road, which is what you're looking at here with sodium chloride, and then you have hydrogen bonding. So let's deal with these separately, not in that order, but in ways that make sense to what we see in biology. And so since we're talking about sodium and chloride and emergent properties, how exactly do they come together? What all has to do with electrons and the rules for electrons. So in chemistry, you may have heard of, and you should have learned about enough of valence electrons. And valence basically has to do with how many electrons are in the outermost shell And is that orbit or shell full or empty, and by how much? If you have no electrons in the outermost orbit or shell, then you have a high degree of valence. You have a lot of empty spots that can be filled, or you can donate what's out there to another atom that's ready to receive it. And that is exactly what happens with sodium and chlorine. Chlorine has 7 electrons in its outer orbit, and it wants 8. It can have 8. It can hold 8. Sodium has the same number of orbits here, but it only has 1. And here's what you need to know about atoms. They want to be stable. I'm saying want like they have desires, but it's the way we talk. They want to be stable. They seek to be stable, and one way to do that is to lose the electron or to gain the electron, to be completely empty or completely full. And this issue of valence, of having openings or spots to be filled, is what allows certain atoms to be highly reactive or not reactive at all. And so this is how this works. And so here sodium is going to donate an electron, making its overall charge more positive because it lost an electron, which is negative. And chloride receives the electron, which means its overall charge now is more negative, but its positions are full. And so you have a cation that's positive and an anion, which is negative. Positive and negatives are opposites, therefore they attract, and so sodium chloride are two atoms that stick together like little magnets. Another fun thing to talk about is the property of water through covalent bonding, and then because of its shape, which we'll discuss later, it acts as a type of molecule that can do some funny things. So we're going to cycle through these in different ways of talking about shape and bonds and electrons. And so water is covalently bonded, which means it doesn't donate an electron or receive an electron. It shares an electron. The thing is that hydrogen atoms are smaller than the oxygen atom, and so hydrogen atoms are sharing the electron with oxygen, but they share it unequally. Hydrogens only have 1 proton, oxygens have 8 protons, oxygens are bigger. So yes, they share the electron, but the hydrogen and the oxygen share it unequally. It's like big brother, little brother. The big brother gets to play the game or drive the car or get the most chicken from dinner or whatever it is, but the big guy gets the most and the little guy gets the least. And what that's going to do for us with water later is create this funny looking shape and create a difference on opposite sides of the molecule, which allows water to do a whole lot of cool things that we rely on in biology. So you can arrange the periodic table in any number of ways. Biology doesn't care about all of them. Like we don't really explore uranium and plutonium in biology. Those are lethal. We don't really explore arsenic, although it's made by living organisms and toxic to them as well. So biology has very, very particular interests in chemistry. It's not all chemistry. It's just certain aspects, but we have to know enough. So this is one way, for example, this picture of how biology rearranges chemistry for its own purposes. I just wanted to show it to you. So let's get some facts down in your notes. Of the 92 natural elements, and there are a couple handfuls more that have been made synthetically in lab, but of the 92 naturally occurring elements on this planet, only about 20 to 25% are essential for life. In other words, they are needed by an organism at some level to continue running chemically and to reproduce as a living organism. In other words, to share enough of that matter to allow life to continue. And then we have a different level of, or category of elements called trace elements, where they're not needed in large enough quantities. They might affect the health or the longevity, of an organism, but they're not needed to make some of the essential aspects, structures, or processes that are needed. And so these are just two types of terms that I need you to get familiar with things that are essential, which means they're needed in abundance for large processes or structures. And then there are trace elements where you don't need a lot, but they are important, but they're relatively easy to get. So, believe it or not, some naturally occurring elements are toxic, as I just mentioned a while ago. Arsenic is made by living organisms, so it's natural, but it is poisonous to other living organisms. And so, be careful with the word organic, equating organic with not healthy or not made by nature. There are lots of terrible things that are made by the natural world. Anyway. Some species, though, have become adapted to toxic environments. So you can put sunflowers in your garden, especially if you live in the suburbs, to soak up all kinds of toxins from the dirt before you go planting your carrots and potatoes. Cattails, we have those in our pond on Founders Campus. And then I work with a biologist who studies killifish down in Baytown and Houston in the Gulf, who not only survive in toxic waters, but they're larger than their siblings in other areas. So they're actually thriving and doing better, which is really, really strange. So life always finds a way. In your notes, I would love for you to know this fact. It's really important. 96% of your total mass is only made up of 4 elements. So this helps you understand what we mean by essential. So I'll show you the trace in a minute, but there are 4 elements that are absolutely essential to making up 96% of your total mass. And here they are. In your notes, I want you to go ahead and draw these circles and letters and dots just like you see them. You can pause the video right now and add this into your notes. I need you to understand the arrangement, where the electrons go, how many orbit shells they have. These 4 elements make up 96% of your total mass, and they're carbon, hydrogen, oxygen, and nitrogen. With these 4 elements, you can pretty much make anything, and we'll go through some large macromolecules that are made from these 4 elements. But looking at these 4, there's a couple of things I want you to know. All life on this planet is carbon-based. It doesn't mean that carbon is the most abundant element in your body. It's not. But it does mean that carbon forms a type of building block, or ultimate Lego, if you will, for building all the major structures that we need. And the reason is due to valence. There's a rule with orbit shells and electrons, these dots inside these rings, and you need to know this rule. In the innermost shell, you can have 2 electrons. In the next shell or orbit, you can have 8. And really rarely, we only go to the 3rd level in biology, which we already discussed with sodium and chlorine. But we're looking at the 2 in the middle, and then you can have 8 on the outside. And if you look at carbon, it has 2 in the middle, but how many does it have in the next ring? Only 4, which means it's 50% full and 50% empty, right? And so that means it has a good degree of reactivity, but it's not super volatile. So oxygen, if you look at it, it has 2 in the inner ring and 6 in the outer ring, which means it can receive 2 to fill up. So that's why you have O2. It's very stable. And so anyway, the less electrons you have in the outermost ring, the more reactive you are. So carbon makes the best Lego. Now in a minute, I'm going to show you a chart, and we're going to find carbon's cousin or nearest relative and ask a question of why not that one, right? So all life is carbon-based. The most abundant element in your body is oxygen. That's just a factoid, but it's in CO2, O2, H2O, and so oxygen is in all of these compounds that are in your body. So that's the most abundant if you wanted to know. So looking at this chart right here, find carbon. It's in the second row of the second shell. Find carbon. It's got 2 electrons on the inner ring, 4 on the outer ring. Now, can you find another element close to it that has 2 electrons on the inner ring and 4 on the outer ring? If you go down from carbon, you can look at silicon. Silicon has 2 electrons on the inner ring and 4 on the outer ring. So why not silicon? Let me make the problem worse. According to current estimates right now, I think it's 0.6%. I have to double check myself, fact check myself, but 0.6% of the entire Earth's mass is made up of carbon. And 67%, if I have that right, of the Earth's mass on the surface, on the crust is what I should say, is made up of silicon. So why did life choose carbon? Well, if you look at the two, what do you notice between carbon and silicon? You should notice that silicon has an extra orbit. It's a little bit larger. It doesn't seem much to you, but keep in mind these Bohr's models are not to scale. Atoms are mostly empty space. And so silicon is significantly larger than carbon. In other words, if life used silicon, all the structures would be bigger. Everything would be bigger, much bigger, exponentially bigger once you start adding up the sheer number of atoms that it takes to make a living thing. And these structures would be too big, gravity would have too great a force on them, their momentum would be too high, they wouldn't work properly, and so silicon doesn't work. So life chose the harder path. And so I think here's a way to fact check me. You can see a number of numbers, a number of numbers. You can see amounts of these elements on the planet. And so if we go through here, this is the percentage of your total body weight. I thought I had, there it is, it's coming next. I'm sorry, I'm talking to myself. But this is in your body, and the next slide is the abundance on the Earth. And so there's the most abundant element in your body is oxygen, and then next is carbon, despite carbon's relative rarity on this planet. And so here are essential elements versus trace elements here listed separately. I love this that you have some copper, and there was even an Olympics advertisement that said everybody has a little bit of gold in them, and athletes know how to bring it out. Ooh, that was so dramatic. So here's what I was talking about earlier. Let's see if I have my numbers close or not. So where's carbon and then silicon, if we can find it? Is it on here? I thought it was, but anyway, well. So carbon is extremely rare on this planet. You can look it up, and then silicon is the more abundant one. And you can see them. I listed it at the top, but I thought I had the numbers here. So anyway, there you go. There's carbon. Within organisms, it's 18.5%, and I don't even see it listed on the planet unless I'm just missing it completely. Whereas silicon is at, there it is, I'm sorry, there it is at 25.7% in the Earth's crust. That's where it's located. So there you go. There's your numbers, and life chose the harder path.